So let's look at graphing logarithms. So this is a big part of the section in Hawks, graphing logarithms. So I just rewrote the definition of log in terms of the exponential. So y equals log base a of x means a of y equals x. So on this function, I plug in x and out comes y. And on the exponential, I plug in y and out comes x. So that means they're doing the opposite, right? They're undoing each other. So the logarithm and the exponential function are inverses. That's what the log was defined to be. It was defined to be the inverse of the exponential expression. And the reason I need an exponential inverse is I need to be able to solve for exponents. Like if I have some kind of equation where the variable's in an exponent and I need to get it out, so I would like to be able to do an inverse, and we did that by creating a function that would undo the exponential. Okay, so the log and the exponential are inverses. So let's remind ourselves about the exponential function. It has a domain of negative infinity to infinity because you can plug in any exponent you want, no problem. It has a range of 0 to infinity because if you raise a positive number to a power, it only is ever positive. And the exponential function never equals 0 because there's no way to plug in a power. There's nothing I can raise, no number of times I can multiply something by itself and end up with the number 0. Okay, so this is my graph of the exponential. It had 3 anchor points, 0, 1, so anything to the 0th power is 1, 1a, which means anything to the first power is itself, and negative 1, 1 over a, meaning anything to the negative first power is its own reciprocal. And then an extra thing about it is it grows really quickly, very quickly. These are our quick growing functions. So knowing what we know about the exponential and what we know about the relationship between inverses, I know that what goes in and what comes out of a function is what goes into its inverse. So the domain of the log is going to be 0 to infinity, and the range will be negative infinity to infinity. So I can only take in I can only take in positive things, and I can output any positive or negative thing. The anchors, so instead of xy, I'm going to use yx. So 1, 0, a1, 1 over a negative 1. So 1, 0, a1, 1 over a negative 1. So this is my logarithm. These, instead of growing very quickly, are going to grow very slowly. All right, so let's actually look at a comparison of a log graph with its exponential. All right, here is my graph. Oops. Here is my graph of the 2 to the x and log base 2 of x. So those guys should be inverses of each other. And then I went ahead and plotted the line y equals x because remember that in a graph and its inverse are symmetric about the line y equals x. So you may remember I actually physically had a little graph and it was like folding it up on itself. So it has the point 0, 2 on the red, 2 to the x, and it should have the point 1, 0, which it does on the blue. My exponential should have the point 1, 2, so right here. And my logarithm has the point 2, 1. my logarithm, or sorry, my exponential has the point -1/2, and my logarithm has the point 1/2 -1. All right, so those are my graphs. Now, just like all of the exponentials look like the red function, all of the logarithms look like the blue function. So here, I'm just going to zoom out super far so you can see. So the logarithm is the blue, and look how slowly it is growing. It looks like it's flat almost. It's not, but it looks like it is. Exponentials grow very rapidly, logarithms grow very slowly. So sometimes it's useful to use a logarithm so you can, talk about something that's growing very rapidly. Sometimes for data that grows quickly, you can plot it not on a regular Cartesian grid, but actually on what's called a log scale, so that every unit is a power increase, 1 power increase. So instead of, one step being 1 to 2, a step would be 1, power of 1, power of 2, power of 3. And that would let you write out this, data that grows quickly and is hard to fit on one page into something a little more manageable. Now, if you have something exponential and then you graph it on a log graph, what that means is, since they're undoing each other, your result should be something linear. So that's a way that you can take something that you suspect is exponential and show that it is visually. You can just put it on a log grid and it can end up being linear. So one other thing I want to do is to look at the graphs that are on hawks so that we can see how those are done. All right, so here's my hawks, and let's go in and look at a couple graph the logarithm. All right, so which of the following is the correct graph? So you have the anchor points 1, 0, A1, 1 over A, -1. So you know what this should look like. All right, so this should contain the points. I'm actually gonna maybe need to write something down for it. Okay. So example. Log base 1/4 of x minus 5. Okay, so this has only a horizontal shift to the right by 5, right? All right, so my anchors, I would start with 1, 0. So A is the base. In this case, the base is 1/4, 1. And then 1 over A, -1. So the reciprocal of 1/4 is 4. So I start with that, and then I shift them to the right by 5. So that means I'm going to add 1. I'm going to add to each x value. So 1 plus 5 is 6. 1/4 plus 5 is 5.25. 4 plus 5 is 9. All right, so I'm looking for a graph that has these points. So I would start with 6, 0, see which one has the number or has the point 6, 0. Which, when I look, let's see, the first one does not have 6, 0. The second one does. The third one doesn't, and the fourth one does. So it has to be one of these. And it also needs to have the point 9, -1. So this one, right? Because as this is going towards 9, it's getting more negative. All right, so it has to be this one. Great. Now because this base was 1/4, this is like doing a reflection. So when we were doing the exponentials, sometimes instead of writing 1/4 to the x, we wrote it as 4 to the negative x. All right, so then when you find the inverse of that thing, that's going to give you this log. So that's why it looks a little bit different from the one we had. You could also look for the point 5¼ comma 1, so that would be right there, which this one has. Okay. So that's just evaluate. Here we go. So log base 2 of x plus 1. So this is just a log base 2, but shifted up 1. So usually it would have the point 1, 0, but now it should have the point 1, 1. So the only one that has the point 1, 1 is this one. So it has to be that. Great. So we didn't even need to write anything down for that. So just like with the exponentials, for doing the logarithms, the logarithm graphs, I would write out your anchor points, do the transforms on them, or you really could evaluate the log at a couple different points, but because they're going to do like kind of strange log bases, that's maybe not as efficient. They are inverses. The logarithms and the exponential are inverses of each other, so their graphs are symmetric, and you know these anchor points are exactly the opposite of the exponential function.